Today in Applied Calculus, we are going to apply the rules that we learned, the three basic antiderivative or indefinite integral rules that we learned, and learn how we can take something that looks like it's more complicated than that, make a substitution, and then realize it's actually just as simple of a problem. So let's recap the three rules that we know. So if you were given a function u to the r, where r is some constant, remember the integral sign and the du are a package deal that go together that say please find the antiderivative, and this would be that reverse power rule. We would add 1 to the power, divide by the new power, and then of course our plus c. Now we do not use this when r is -1, because if r was -1, that's 1 over u, and that has its own rule. The antiderivative of 1 over u is ln of absolute values of u plus c. Also, I hope that if you didn't realize it then, you would catch it, because if you had done this reverse power rule with a -1, you would end up with u to the 0 over 0. You'd have division by 0. So hopefully, if you see that, it'll be another line of defense for you to realize, oops, I should have treated this as what it is, which is the reverse, ln rule. And then we have e to the u. So if you have e to the u du, then it's its own derivative. So it is just e to the u plus c. So you will notice that I had u's instead of x's here. Usually when I do this in class, students don't even skip a beat. I ask them what the answer to this is, and they tell me u to the r plus 1 over r plus 1. So it doesn't matter what our variable is, as long as these match, the u and the du. As long as they match, then it's the same rules, okay? So to do one of these substitution problems, we're going to have to look at our notation a little bit different. So we had that Leibniz notation for a derivative that was dy dx. And at the time we said it is not a fraction, you can't treat it like one, it's just notation. But I may have alluded then that later we might violate that a little bit, and we're getting there. So these are interchangeable, dy dx and f prime of x. So if we actually do treat this a little bit like a fraction and multiply both sides by dx, then we can say dy is f prime of x times dx, okay? So all we're going to be doing here is just practicing. Instead of writing dy dx equals the derivative, write dy equals the derivative and put the dx on the other side. It's essentially multiplying both sides by dx. So if I had a function y, or f of x, equals x to the 4th, we are used to saying, okay, so dy dx is 4x cubed. Be careful, because this is a regular derivative we are doing here, okay? And so in this section, we are going to be switching back and forth between derivatives and antiderivatives, and you need to be careful about which way you are going when you are applying things like the power rule, or is it the reverse power rule, right? So this is a derivative, so I bring down the power, subtract 1 from the power, and all we are doing, all that's new here, is we're multiplying the dx on each side. But I don't really want to show this every time. What I can start doing is just saying dy equals 4x cubed, and let me just put the dx over there. Or if a function was named u, so if u, is the name of our function ln of x, then du dx would be 1 over x. But instead, let's just write du equals 1 over x dx. And you'll see why we're doing this in just a second. Or lastly, if u was e to the x, then instead of writing du dx equals, this is e to the x squared. So this derivative would need the chain rule, e to the x squared times 2x. I can go ahead and put the dx over here and have du equals e to the x squared 2x dx. So that is all we were doing here. For one, reminding ourselves that we are going to be doing some regular derivatives, not just antiderivatives, and then that notation can be used as a fraction, in fact, and that the dx can be put with the other side. And we're going to see why we care about that on the next page. So for one of these substitution problems, you kind of just need to see one the first time, and then we'll establish some patterns and talk about what we're doing. But I do think, and hopefully you'll see as I explain each step and I've color-coded things, I do think this looks daunting in the beginning, but actually can be quite easy and borderline fun if you allow yourself. But just reading through in a textbook and seeing all of it there at once is not necessarily helpful, but hearing the thinking that's going through each step hopefully will help you. So why were we saying du equals something with a dx on the end? Well, when we learned this notation, we said, oh, the dx is just a package deal with the integral sign that says, please integrate, please find the antiderivative, and oh, by the way, your function is x, your variable is x that your function is in. But now the dx is going to be really, really important, and we're going to have to keep track of it. So what you're going to see is a problem that is not as simple as one of the three on the first page. But I don't give trick questions, okay? So we only know the 3 rules on the front page. If you see a problem that doesn't look exactly like one of those 3 rules, there must be some other way you can handle it. So I do see an e involved, but the only thing I know about e is if it is e to the x or e to the u, but not if it's got other stuff around it. So what we're going to do is make a substitution so that we can realize it is just one of those 3 easy cases that we already know. So we are going to pick a u. Now, I don't know if I said it on the first page yet. This method is basically the reverse chain rule. And if you think about the chain rule, it was all about the derivative of the inside function. You had to do times the derivative of the inside. So if this is the reverse chain rule, we are going to be focusing on the inside function again. So we will talk about how you know how to choose u. It takes kind of practice and seeing some to come up with it, but we'll have some rules or guidelines to help you pick u as we go forward. So don't get too worried about that just yet. But do focus on the inside function. Well, if I look here, remember the inside of an exponential function is its exponent. That's what you plug into it to do something. So x squared is this inside function. For now, I'm just going to give that rationale for why I chose it, is that it is the only thing where I see that it's inside of another function. So if I pick that u to be x squared, we're going to do what we warmed up with on the last page and take its derivative du. Now I could do that in 2 steps and say du dx equals x squared and then move the dx over. But what I will get is that du equals, the derivative is 2x, and then I've brought the dx over, so 2x dx. Now you're going to see why the combination of, hey, that dx matters, and let's move that dx to the other side in our du dx notation, it's all coming together. So what we're going to do is just to help us see it, there'll be many times where you might want to just rearrange things. It is typical for us to put the 2x or that sort of thing out front, but right now I want to group things together that go together, and so multiplication's commutative, right? The order doesn't matter. I'm allowed to do this. I'm just going to switch the order of the multiplication and put the 2x back with the dx. Why did I do that? Well, because 2x dx is exactly the du that I was talking about, okay? So I have things so that I see e, and this was my u, and 2x dx is my du. So I rearranged it to get those things together, and then I'm ready to substitute. So this is called integration by substitution. And so I've color-coded things for you throughout. So this was my u. It is a fact that u is equal to x squared. So I can substitute at any time x squared in for u or u in for x squared, and we will do both. Also, it is a fact that given that u, its derivative du is 2x dx. That means if they are equal, I can replace one with the other all day long, and it's fine. So I wanted to show where those things are right now when I rearrange things. I have e to the, and x squared was my u that I chose. And then I have 2x dx, and that was my du that I chose. So I am then ready to actually substitute. E to the x squared was u, and then 2x dx was du. So I have e to the u du, and I know how to integrate that. It's right there, e to the u plus c. Done. So the answer then, I'm going to integrate. Now remember that the integral sign and the du are a package deal that say please integrate. So I've done that. What is the antiderivative of e to the u? It's e to the u plus c. But remember, the original problem did not have u's in it. U tends to be what's used in most books. They usually call it U substitution. But we did just pick it. You could have picked P, I guess, for Palm, your favorite professor, or whatever, right? But that was something we introduced into the problem. The problem had x's. So that's the very last step, is that we need to put it back into x's. So I'm going to rewrite as my final step, well, what was U remember, these are interchangeable. I mean, it's an equality. So u was x squared, and that's good because the original problem was given to me with x's, and so I have e to the x squared plus c as my final answer. So what is the goal? The goal is to take something that looks like it's too complicated, does not look like it's one of the three things we know, make a substitution so that we can see it is in fact one of the three things we know, because Professor Palm does not give trick questions, okay? And then it's very easy to integrate and then put it back into x's. So remember, you can always check your answer by taking the derivative. If you pause for a second and go do d dx of this with the chain rule, because you will need that, you would get e to the x squared times 2x, and then of course plus 0. And so that is the integrand that we started with because the order of the multiplication doesn't matter. So this, as mentioned, is called u substitution, and you can think of it as the reverse chain rule. So I know you're thinking, oh, she's making it harder because we're not going in order, right? We did the basics and then the product rule and the quotient rule and then the chain rule. When we did derivatives, well, it turns out actually that the reverse product rule, call it integration by parts, is actually harder than the reverse chain rule. So I promise I am going in order. Okay, so as I said, we're just going to do a lot of examples and work on how do you choose that u. Because once you have that down, the whole idea is make a substitution. It's now one of the three things that you know that you mastered and worked hard on in your last section, and then you just do the antiderivative and put it back into x's. So keep in mind the inside function idea. When I look here, think, what is inside of something else? Well, when it is like this with big parentheses, it's a pretty nice, easy choice. There is literally something inside of these parentheses being raised to the third power. It is x squared plus 1. And so that is going to be what I choose to be my u. So I'm going to let u be that inside function x squared plus 1. Now, something that we need to be really clear on from the very beginning is that we do not just get to randomly choose what du is. We pick u, and then everything else is determined from there. Now, because all of our early problems are so nice, people start thinking that I picked the du from the problem, and that is not the case, and I'll show you by the end. Okay, so once I've picked u, du is that guy's derivative. Don't even look back over at the function again. This is your u. Tell me its derivative. Du would be 2x plus 0, or 2x. And remember, instead of saying du dx, I can go ahead and put the dx over here. So u's derivative, du, is 2x dx. Now what I'm going to do is, as we did before, kind of rearrange just to get things together. So rearrange to make the substitution easier to see. So I grouped the du things together, and then the u, okay? And then I wrote an extra line so that you could see the step-by-step, but you could do it right on this step. Now I want to substitute. So notice that this x squared plus 1 is my u, and this 2x dx is my du, so I can replace those quantities with those values. So if this is u, then instead of x squared plus 1 cubed, I can simply write u cubed. And if this is du, then instead of 2x dx, I can write du. Now I have a very simple integral, the integral of u cubed du, where the variables do match because they must in order for me to integrate. And it says, please find the antiderivative. It is a reverse power rule problem. Now it looks like one of the three on the front page, the top one, namely. Okay, so I add 1 to the power, divide by the new power, have my plus c. But remember that the original problem did not have u's in it. That was something I used to show my work. And so I do need to get it back into x's. What was u? U was x squared plus 1. So we actually have x squared plus 1 to the 4th over 4 plus c. So you can see we make a substitution from the x squared plus 1 to the u. And then once we have used that u form that makes it an easier looking antiderivative and done the problem, then we put it back into x's. So we do substitute in both directions. Now, before you ask, I don't end up having to do that, like the red ends here, right? Why does the red end? Well, remember that the integral sign and the du are a package deal that say, please find the antiderivative, and once you've done that, they disappear. So interestingly enough, it usually isn't until this section that students say, where did the du go? And then I always call them out and say, well, nobody asked where the dx went. You must be discriminating against, x's versus u's. And so it never seemed to bother us before when it was x, or either just we hadn't done enough to realize it. But again, the integral sign and the d whatever are a package deal that say please integrate, so once we've done what they ask, they're no longer there. So whether that's a dx or a du, that's still the case. I think we just have more ownership of du because we actually wrote it and we did something with it, and maybe that's when we notice. But it's a question that needs to come up in your head, and then you can deal with it. Okay, so here's another one. Well, what would you say is inside here? Well, there's something clearly inside a root, and so that is indeed going to be our u. So we will let the inside of the root be our u. Then just looking here, we will take its derivative du, and I get 3x squared dx, okay? So that is my du. Now that happens to be up here in the problem, but that's only because these problems are perfect and nice. That is not how I picked it. I picked u because u was an inside of the root, and then just looked at that u to take the derivative and get du. Then I'm going to rewrite it because I do need to have it in a nice form where I see that that's actually a 1/2 power instead of a root. And I also want to group things together. So if my du is 3x squared dx, now when I do look at the problem, I do see a 3x squared and I do see a dx, so let's get them together. And then we will be ready to substitute and solve. And so just to show you, I've just recopied it and color-coded it, that we said x squared plus 1 was our u. So instead of x squared plus 1 to the 1/2, I can simply write u to the 1/2. And 3x squared dx was our du. They are equal. They are interchangeable. And so I will replace it with du. Now my variables match up. So I would not write u to the 1/2 3x squared dx. I couldn't do anything with that because the variables don't match. But here the variables match. Now I see it is simply a reverse power rule. I add 1 to the power and divide by that new power, or multiply by the reciprocal. So again, we talked about how you can either show both of these steps, or you might do enough that when you see it's a fraction that you're going to be adding 1 to, you just go ahead and add 1 and then multiply by the reciprocal, whichever one is good for you, okay? And we do get our plus c. So what we have is 2/3 u to the 3/2 plus c, but I need to rewrite it back in x's, or whatever variable was given. So rewrite the answer with x's because you were given the problem with x's. That's kind of a good general rule. So 2/3 x cubed plus 1 to the 3/2 plus c, or if we were not to use fractional exponents, then we would use roots. It is power over root, so it's a square root and a cube power. So we have 2/3 the square root of x cubed plus 1 cubed plus c. If you take the derivative of this, it will require the chain rule. That makes sense because our antiderivative is the reverse chain rule, and so to check it, we would need the chain rule. And you should find that you get the integrand, right? Everything between the integral sign and the dx if you actually do that work and check it. All right, looking at another one. So I'm trying to show you a variety so we can get good at picking what our u should be. Do you see an inside? I do see an inside. It looks a little weird because I see a fraction 2, but there is clearly an inside. ln of x lives inside the 2, the squaring. Okay, so that's going to be our u. Then its derivative du, just looking here, is 1 over x dx, and I'm ready to substitute. So I did rewrite it. And this one you want to get good at, because anytime there's the x in the bottom, it is very helpful to realize this is what that means. So if I wrote it over 1 here, remember when we multiply tops and multiply bottoms for fractions, for multiplying fractions, so I would get back to ln of x squared over x. So it really is equivalent, but it lets me see the 1 over x dx as its own thing so that I can make it du. So now we have ln of x squared, but ln of x was our u, so that's just u squared, and then 1 over x dx was our du. So I have now made a substitution so that I can see it actually is a simple integral, one of the 3 on the front page that are the only 3 I know, so it has to be one of those. It is reverse power rule, so I add 1 to the power, divide by the new power, and add my c, and then write it back in x's. So they didn't give me u, they gave me ln of x. I should write it that way. ln of x all cubed over 3 plus c. Okay? So when our u is ln of x, we end up seeing a 1 over x, a x in the bottom somewhere else, and that's going to be something that we notice. All right, now this one and the next one are going to be purposely similar, but obviously different in some way, and we want to compare. So this is the first one where there is not a clear parentheses or root that another function lives inside. So this is the first one where just that idea of inside function isn't really helping us. Well, still, I only have two choices. So I'm trying to choose u. U is either going to be the top or u is going to be the bottom. If I choose wrong, the world's not going to explode. So let's just try it. If I thought u was the top, then u would be 4x cubed and du would be 12x squared. All the rest of the problem usually ends up having something to do with my du. Not exactly necessarily, but close, we'll see. And 12x squared is nowhere here. I still have nothing I can do with the x to the fourth. It doesn't look like it's working out like other problems. So let's switch it around. What if u was the bottom? So if u was 1 plus x to the fourth, then du, its derivative would be 4x cubed dx. So we're going to get to where hopefully you don't feel like you're just guessing and trying it, but you can, right? There were only two choices. It wasn't clear which one to choose, so just try one. If it didn't make it look like one of the three problems on the front page that are the only three antiderivatives we know, then it must not have been the right choice, so you pick the other thing, okay? So we ended up choosing the whole denominator, and that is going to be key later. 1 plus x to the fourth, and its derivative du is 4x cubed dx. So now with some rewriting, we will see that that was the right choice. So again, separating out a fraction like this is going to be really important. It's basics of fractions. If you're not good at it now, do some practice because being able to see that is very helpful. So again, because I could put this over 1 and multiply tops and multiply bottoms, and I would indeed get back to where I started. So these really are equivalent to each other. But now I can see that it's 1 over 1 plus x to the fourth times that 4x cubed dx, and that's good because that was my du. So I have 1 over my u du. 1 over u du. Well, that better be one of the three rules that I know on the front page. And it is. Who has a derivative that's 1 over u? ln of u. Remember those absolute values. Those will show up in a symbol palette in your homework software. So ln of u plus c, and then simply rewrite the answer in x's because they gave it to me in x's. So instead of ln of u plus c is my final answer, it's ln of 1 plus x to the fourth plus c. So we rewrite it to help us see and make a substitution. Then it is a very simple integral, that's the whole point. And we write the antiderivative and then put it back into x's. Okay, so remember I said I was going to show you a similar one. So look at the one we just did. It was 4x cubed over 1 plus x to the fourth. This one also has 4x cubed in the top, and it does have something with 1 plus x to the fourth in the bottom, but it's that quantity squared. So the difference is, and you could argue this one's actually easier, but there's something else I want to compare, is there is a clear inside here. So I know in the last example we picked the whole denominator to be our bottom. That's because that's all there was. But here I am going to pick just the inside of that denominator. So it is again going to be 1 plus x to the fourth, but I'm not going to have it be 1 plus x to the fourth squared. And if you did choose that and took the derivative correctly with the chain rule, you would see it makes it way complicated. It does not help simplify the problem. So we are picking that inside function, the inside of the squaring parentheses as our u, and then du would be 4x cubed dx. And so I rewrite it, again separating out that fraction. And this time when I make my substitution, so this is 1 over actually u squared, and then of course, yes, that was my du. All right, so just to color code it, as we have been doing, there was my du. I recognize that that was my du, so I replaced it with actual du. And now I do have the variables matching. But this is a power other than 1 in the denominator. So it needs to be rewritten up in the top with a power as u to the negative 2. And it will be a reverse power rule problem. Whereas our last problem ended up being the antiderivative was ln, okay? So what that power in the denominator is on the quantity matters. So here it is a reverse power rule problem. We will add 1 to the power and divide by the new power. And then we have plus c. We can write what that actually means. The negative is there, and then this negative exponent means the u should be in the bottom, and now it's a positive 1 power, plus c. And then I can put it back into x's. So negative 1 over 1 plus x to the fourth plus c. And I just rewrote it once without the colored boxes because you definitely don't need to have those colored boxes in all your things. I just wanted to help you to follow what's happening with that color. Okay, so here's one more. Now, we've been talking about insides of parentheses, so there's a reason we're looking at this. If you chose u to be 5x because it's inside parentheses, okay, u is 5x, then du is 5. It doesn't help at all. What I would end up with is ln of u over x dx. I'm not able to substitute everything. So you don't always want to just think about inside. But we did talk about how if you have an x in a denominator, it's probably because you took a derivative of ln of x and got 1 over x. So it turns out if ln is involved, we want to pick that ln function. Now remember, I cannot literally pick just ln. It always has to be ln of something. So I'm picking ln of 5x, that whole function. It is not ln times 5x, it's ln of 5x. So that's going to be my u. And then be careful here. I do not want you thinking the derivative of every ln problem is 1 over x. However, in this case, because that's a constant, it's 1 over 5x times, so it's 1 over the inside times the derivative of the inside. And so you get the 5's to cancel, and it is 1 over x dx, okay? Okay, so our u is ln of 5x, and our du is 1 over x dx. So we're going to separate those things out again. So we have ln of 5x times 1 over x. Again, multiply tops, multiply bottoms. It really is what we had before, and we need to be comfortable doing that. And now I can see that the ln of 5x was my u, so I can replace or substitute it with a u. And the 1 over x dx was my du, and so I can replace it with du. So here I am integrating simply u to the first. Okay, so if you need to write that hidden 1 power, you can. And then it is a reverse power rule problem. So notice that the integral sign is gone here, as is the du, because I'm doing what it asked. I am adding 1 to the power and dividing by the new power to do the reverse power rule, and then I get my plus c. Then I simply put it back into x's, and remember that u was actually ln of 5x, so I write ln of 5x over 2 plus c. So we rewrite it back in x's. So that is going to be a rule that we're going to see. It's not all just about picking insides of parentheses, but we are seeing that if there's an ln involved, most likely choosing that whole ln function to be your u is going to work out. Now, not necessarily always, but it's a good guideline. And so speaking of guidelines, through these many, many examples that we've done, and I hope that they were helpful, you've kind of seen everything you could possibly see, all the different cases. Then we've realized some things that will help us to pick our u and not feel like we're just guessing what our u should be. The overarching principle is it being an inside function, but we saw that that doesn't always quite mean, it's not quite as obvious as we would like it to be. So there's only 3 derivative rules, okay? So it has to end up being an e to the u problem, a 1 over u problem, or a u to a power problem. And so that kind of helps us too. So if there's an e in your problem, that's going to be what kind of integration it is e to the u. So you need that exponent to be your u. You need it to end up looking like e to the u du. Okay, so if you have an e in the problem, then choose the exponent to be your u, and you'll end up with one of those problems, okay? Then we also realize if there's ever an ln in the problem and an x in the denominator, because then that derivative gave you something involving 1 over x, choose that entire ln function to be your u. Now, I think we actually saw 2 cases, so that it probably won't be an e problem, it would be one of the other 2 there. You could have ln of ln, but I don't typically do that. Okay, if there is a quantity being raised to a power or under a root, which we know is in fact being raised to a power, a fractional power, choose that quantity. So that's actually the easiest one, but I do kind of want you to check these other things first, because if there's an e there, it's definitely that. And we do want to kind of separate out the ln, because we saw that we don't want to just pick the parentheses that represents its inside necessarily, that we want to pick the entire ln function. So I do have a method to my order here, okay? So if there's a big quantity with power or root, then you're going to choose that to be your u. And then if there is a fraction and it doesn't fall into one of the last 2 cases, so it wasn't where there's an x in the bottom and an ln in the top, and it wasn't where you have a parentheses being raised to a power like 2 or 3 or 4, that there you need to rewrite it as that to the negative 2 or 3 or 4 up top, then you want to choose the denominator. And so that would be like our example that was 4x cubed over 1 plus x to the 4th, where there wasn't a parentheses on it. Then we chose the whole denominator to be our u, and that ended up being an ln of u problem, right? So it ended up being one of those. And in here, we actually saw a couple different things happen where we could end up with it being a reverse power rule or a different kind, but this will help you to pick your u. So always remember, and I've tried to stress this the whole time, du is always the derivative of whatever you pick to be u. You choose u first, and then there are no choices about du. It is the derivative of whatever you pick to be u. You do not just get to pluck du out of the problem somewhere. It may look like I've been doing that, although you've been watching my steps and hearing my reasoning, so hopefully not. But if you just looked at something on paper, it might look like that's what they're doing. But that's only because these problems have been perfect and nice, and they won't always be. And so that leads us to our last couple examples. So sometimes we have to do a little bit more thinking to make it work out. These all worked out perfectly. Once we picked our u, our du was exactly in the problem, but that won't always happen, which is what I was warning you about. This will also let us practice our picking u's, okay? So when I look at this, I see an e, and we said I should let that exponent be my u then. So I let u be x cubed, then its derivative du is 3x squared dx. I did not look over here. U is x cubed, its derivative du is 3x squared. End of story. We've done derivatives for months now, okay? So if I reorganize this like we've done to kind of group things that will have to do with our du and group things that have to do with the main part, our integrand, then I've left a blank there on purpose so I can go back and show you kind of how I would show the work. We cannot substitute right now because du is not an exact match. I cannot all of a sudden say there's a du here, because there's not. I don't have 3x squared dx. I only have x squared dx. Now there are a couple different methods for showing this. I'm fairly certain your book does the other way, so I am purposely showing you this way. And for these simple ones, I think it can be very nice. But you can pick whichever method you want. So you'll have my examples and you'll have their examples, and you can pick the method you like. So I do something that I call compensating, all right? And they might teach both, I'm not sure. So here, I do not have 3x squared, so I cannot substitute. But what I can do is put in a version of 1. I can't change the problem. I can't just shove a 3 in there to make it work how I'm hoping it will work, because that would change the problem. But I can multiply by 1 all day long. So I'm going to choose a certain kind of 1 that is 3 over 3, or in other words, 1/3 times 3. If I do that, I can separate out the 1/3, which is just a constant out in front, from the 3. So they're still both there, so it is 1 if I multiply them. But now, by leaving the 3 in, I see my du. So now here's my e to the u, and here's my du. Now just to go back and show you, and I'll show you on the next one as well, the way that I would do this is I would write the problem and leave a blank here and say, what am I missing? I'm missing a 3, but I can't just change the problem. So if I put a 3 in, I also have to put a 1/3 in. So in terms of actually in live time as I'm writing, that's what I would do, is I would rearrange things, leave a blank where I realize there's an issue. I was missing the 3. And then I would put the 3 in that I'm missing and compensate on the outside with its reciprocal so that I am effectively multiplying by 1. But I'm putting the parts that make up that 1 where I need them to be to make this work. So once I am there, I now do have exactly du, 3x squared, underlined here in red, and I do have exactly u, x cubed, underlined in green. And so I have 1/3. Now that's something you have to keep in mind. That's now there for the long haul. It's going to stay there the rest of the time. It had to be present for you to put that 3 in and make that substitution. So I now have 1/3 e to the u du, and it is one of our easy antiderivatives. So 1/3 stays. Antiderivative e to the u is e to the u, and then plus c. And then, of course, I need to put it back into x's. So 1/3 e to the x cubed plus c. Okay, so that's as bad as they get. They There are some other things that could happen, but for us in this class, we are only ever going to have that our function is off by a constant from what du actually is. So in other words, we were missing the 3 here and we had to fix it. So let's look at another example. We said when you have a fraction and you don't see ln's and you don't see big exponents, big things raised to exponents, pick the whole bottom to be your u. So I'm picking the bottom to be u, then its derivative du is 8 dx, right? It's 0 plus 8 dx. Just looking at u taking the derivative. Well, I don't have 8 dx. So it's missing the 8 that I would need to truly substitute. I cannot all of a sudden say this is 1 over u du because it's not, because it doesn't have the 8. But I can put in the 8 that I was missing and compensate on the outside with a 1/8, so that effectively I'm just multiplying by 1, but I'm putting the pieces of that 1 where I need them to be so that I really do have du, and I can really make my substitution to make it look like one of the 3 simple cases that we know. So there I put in my 8, compensated on the outside with the 1/8. Now I really do have the 1/8 must stay 1 over u du, and now that is something I know how to integrate. 1/8, the antiderivative of 1 over u is ln of u plus c, and then put it back into x's. So that's as bad as it can get. So one more. So we saw one with e, we saw one with ln. Okay, and so this one happens to be another e. So if there's an e here, then I will choose that exponent to be my u. That's 7x plus 5. Then its derivative is 7 dx, but I don't have a 7 dx. And so if I have e to the 7x plus 5 dx, I would write that with a little extra space and then say, oh, I was missing the 7. Let me put it in. But to do that, I have to also put in a 1/7, compensate with a 1/7. Now the 1/7 is going to hang out, but I am able to substitute. This is e to the u, and this is du exactly, so I really am allowed to substitute. And so now we have 1/7 e to the u plus c, but putting it back into x's, it's 1/7 e to the 7x plus 5 plus c. So remember, the integral sign and the du are gone here. I really did find the antiderivative, but the antiderivative of e to the u is e to the u. So I really did do it, but it's a cool one, so you almost don't notice, and then put it back in. So we do have, what we're going to see is that if you have something that doesn't look exactly like one of our 3 basic rules, then you will be able to make some sort of substitution using those guidelines that we discussed, so that once you put it in u's, it does look like one of those nice 3 rules. The only place that could be a little bit different is if you just were missing a constant from what you're expecting your du to be, and we've talked about one way to compensate for that. Okay? So practice with this. What you'll see is in later sections, you could have just a regular old antiderivative problem, or you could have one where you need a little substitution in the middle of a bigger problem. So practice on that, and remember, there's no trick questions. It has to be able to look like one of the things on the front page. So think about how you could choose your u, and then find your du from that to make that happen.